Okay, let's unpack this. We're doing a deep dive today into a really specialized piece of tech. It underpins, well, pretty much all quality control and engineering integrity across countless industries. We're talking about the load cell. If you work in R&D, manufacturing, metrology, you know this sensor is absolutely crucial for accurate force measurement.
It's the foundation, really. And what's fascinating, and our sources really back this up, is how long these things can last.
Surprising.
Yeah, we see high accuracy cells, running tests reliably for decades.
And that's really the core of our mission today. We want to give you a shortcut to maximizing that lifespan.
Right.
Because the consensus is clear. These sensors are built tough, but without meticulous maintenance, that precision, the real reason you bought it, it will inevitably degrade.
Exactly. And that's the tension we have to start with. Load cells are, they're engineering marvels. They've got exceptional design, precise machining, materials chosen specifically for stability. They are engineered to be reliable.
So they should be immune to failure then.
Highly resistant, but never immune. At the end of the day, they're still electronic devices. And they're susceptible to two main things: being pushed past their physical limits, and of course, environmental conditions that just mess with their internal stability.
Okay.
So our goal is to dive into those vulnerabilities and, maybe most critically, identify the single most important thing you could do to maintain both function and accuracy.
So let's start with the things that actively sabotage your sensor. The danger zones, if you will.
Good way to put it.
If we understand the risks, we can mitigate them. We're calling this section 1, the 5 killers. These are the most common ways a load cell fails, or even worse, starts giving you bad data.
And prevention is, it's exponentially cheaper than dealing with data corruption or replacing equipment.
Let's start with the big one, the one that's often the hardest to control in a dynamic testing environment: overloading.
Yeah.
This is consistently cited as the single biggest factor in premature sensor failure.
It is. And it goes beyond just, snapping the device in half. When a load cell is overloaded, even just once, it can exceed the elastic limit of the material. That leads to something engineers call permanent deformation.
And if the shape is permanently changed, even just a tiny bit, what does that actually mean for the next 1,000 measurements?
Means you've just introduced hysteresis and nonlinearity. The output curve isn't predictable anymore. The material sort of retains a memory of that excessive force.
So it won't return to zero?
Not reliably, no. And once that happens, the data is compromised. If the deformation is bad enough, even a top-tier calibration lab might not be able to fully salvage the cell.
So the takeaway isn't just common sense like pick the right capacity, it's understanding that there's a non-repairable window. You have to oversize the capacity for your peak expected load, or use serious overload protection to avoid those microfractures that just ruin the material.
Precisely. The second killer is related, but it's caused by quick, blunt events. Mechanical damage.
Physical trauma.
Yes. This isn't necessarily too much force in the application itself. It's,
like dropping the sensor or a sharp impact during installation.
Exactly. Think about the components inside. They are extraordinarily fine-tuned. A hard drop or even just constant excessive vibration can shift those delicate internal components, or it can damage the bond between the strain gauges and the sensing elements.
So the outside might look fine.
The housing might look perfect, but the internal alignment is shot, and that immediately throws the sensor out of calibration.
Okay, that covers the physical side. Let's move to the environment, which I imagine works a bit more slowly but can be just as devastating.
Oh, absolutely.
Killer number 3. Moisture and corrosion.
Water is just a nightmare for any electrical resistance device. In damp or wet environments, moisture gets in and causes internal corrosion or these slow electrical shorts.
And what does that do to the signal?
Well, the corrosion changes the impedance of the electrical pathway. So you start getting unstable readings or maybe a continuous signal drift. It just goes haywire.
So if you're installing a cell outdoors or in a washdown area, you have to be actively looking at that sensor's IP rating, the ingress protection rating.
It's not a feature, it's a requirement. You cannot just assume the ceiling is good enough.
And that's closely related to our 4th killer, right?
Temperature extremes.
So if a load cell is designed for room temperature, why is putting it in a thermal chamber so dangerous?
It all comes down to thermal expansion and contraction. The materials inside, the gauge element, the wiring, the bonding agents, they all react differently to shifts in temperature. And if the temperature compensation circuitry isn't perfectly matched for that application, the internal stresses will change the resistance of the strain gauges,
Leading to?
massive instability, huge errors in the output signal.
So a high-temp load cell isn't just about surviving the heat. It's about maintaining electrical stability while its parts are literally expanding and contracting.
Exactly that. You have to use sensors specifically designed to stay compensated across that entire operational range.
Okay. Killer number 5 wraps it up, and this one is totally invisible. Electrical interference.
EMI and RFI, electromagnetic and radio frequency interference.
And this comes from things like, what?
Often motors, large power cables running nearby, maybe poorly grounded instruments. This interference creates these little phantom voltage shifts on the highly sensitive signal wires coming out of the load cell.
And since the whole point of the load cell is to translate force into a tiny voltage change, that noise basically looks like a force measurement.
You got it. You get distorted or corrupted readings that has nothing to do with the actual load you're applying. The main defense here is just robust, clean grounding through the whole system and using properly shielded cables. You have to protect that signal.
It really sounds like even the best sensors are in this constant battle with physics and the environment. But knowing those risks, the million-dollar question becomes, how do we actually spot the damage early, before the data turns toxic?
Right.
Which brings us to section 2, 5 quick checks.
These are practical, actionable steps for you, the user, that you could perform right now to gauge the health of your sensor.
And step 1 is still critical, even for professionals. Visual inspection. We're not just looking for a major break here. We're talking about case integrity.
That's the key. You're looking for tiny signs of stress, swelling, rust, corrosion around the cable entry points, or dents that might indicate a shear force it wasn't designed for.
And if you see that,
If you see clear evidence of physical trauma, you have to assume that sensors' traceability and its baseline accuracy have been fundamentally compromised.
okay, so step 2 gets into the electrical baseline, the zero balance test.
This is a crucial check for integrity. With absolutely no load applied, and this is critical, with all fixtures removed, the load cell has to read 0.
And if it doesn't?
If it fails to return to 0, that signals internal issues. It could be permanent deformation from an overload you didn't even know about, or maybe an internal short that's changed the electrical symmetry.
Makes sense. If the sensor doesn't know where 0 is, it can't possibly tell you the correct load.
Nope.
Third, we move to a verifiable accuracy check, the load test.
Simple concept. You apply a known standard weight, a verifiable traceable reference mass, and you immediately check if the load cell reading matches that known value within its spec.
So if your sensor is rated for, say, a 0.05% accuracy and it's reading 0.2% off.
You've got a major problem that needs to be addressed right away.
Okay. For those who want to get a bit deeper into the diagnosis, we have the 4th check, which is more technical, bridge resistance tests.
Yeah, this is where we're looking at the heart of the sensor, the Wheatstone circuit.
Can you explain that a bit?
Sure. For those who aren't familiar, it's just a specific configuration of 4 resistors or strain gauges inside the load cell. It's the part that converts the mechanical strain, that tiny physical movement, into a measurable voltage change.
So this resistance test checks the health of those individual resistors.
Exactly. It can help reveal internal electrical issues, like a broken wire, a short, maybe contamination that's affecting one of the 4 arms of the bridge. It can often pinpoint where the electrical failure is, not just that a failure happened.
And finally, the 5th check, which gets at stability over time, thermal evaluation.
Right. Here, you're just monitoring the load cell's performance as the temperature around it changes. This is really to expose any potential thermal stability issues, especially if you think the internal temperature compensation circuitry has been damaged or is starting to drift.
And a sign of that would be?
Wild fluctuations in the reading as the temperature changes. If you see that, you've got a stability problem that will absolutely ruin any long-duration test.
So if you run these 5 checks and you find any inconsistency, a 0 drift, a weird load reading, visual damage, what is the immediate imperative?
Stop using that sensor for critical data collection.
Yeah.
That device needs a professional evaluation to see if calibration can fix it, if a minor repair is possible, or if, sadly, its lifetime is just over and it needs to be replaced.
So never push a failing sensor.
Never. The cost of corrupted data will always outweigh the cost of an investigation.
Which brings us perfectly to the core mechanism for fighting all these things, the process that ensures decades of performance. Section 3 is about the single biggest factor in long-term sensor health, the calibration imperative.
This is it. This is the preventative maintenance schedule that keeps your sensor honest. Calibration is the active defense against that natural aging, component shift, and signal drift we were talking about earlier.
And it's more than just a box to check for an audit. It's an early warning system. Why is this so critical for longevity?
Well, it serves a few roles. First, early detection of anomalies. Calibration will catch subtle issues like minor shifts in linearity or the early effects of environmental exposure, long before a user would ever notice them during a quick zero check.
And catching it early prevents it from escalating.
Exactly. You prevent costly test failures or downtime. It also provides that crucial reaffirmation that quality systems need. The process realigns the load cell with known, verifiable standards, and it confirms its current accuracy profile. This ensures compliance. Regular documented calibration is just mandatory for maintaining quality requirements in any regulated industry. You need that traceable data for every audit.
I think a key insight here, one that often gets overlooked, is the difference between calibration and adjustment. Are they the same thing?
Great question. And no, absolutely not. That's a really common point of confusion.
Okay.
Calibration is the process of comparing the sensor's output against a known, highly precise reference standard. It's done to determine the magnitude of the error. It tells you how far off the reading is.
An adjustment.
Adjustment is the act of physically or electronically modifying the sensor's output so that it reads correctly again.
So you have to calibrate first to figure out what the problem is, and then, only if needed, you adjust to fix it.
Precisely. And in a world-class lab, that entire adjustment process is meticulously documented.
Let's talk frequency. Annual calibration is sort of the standard recommendation, right?
That is the minimum baseline, yes. However, if you're doing high-cycle fatigue testing, or if the sensor is in a really harsh environment, or if your application involves high-stakes, high-risk data,
You need to do it more often.
you should absolutely shorten that interval, maybe to quarterly or every 6 months, just to maintain the highest level of data fidelity and traceability.
And for those who need that defensible data, what does world-class calibration quality assurance actually look like?
It's a rigorous process, and it's fundamentally tied to national standards. It involves using what are known as gold and platinum standard reference load cells. These are sensors that are maintained in the lab, and they're routinely certified by the highest metrological organizations, like NIST in the US.
So those reference cells are the gold standard. They provide the known value you're comparing against.
They do. They're ultra-precise measurement standards. The calibration process then couples these standards with metrology-grade test stands and proprietary software to deliver data that is NIST traceable.
And that traceability is everything.
It's the defensible proof that your sensor's accuracy is tied directly back to the international system of units.
That brings it full circle, back to longevity. How does this annual rigorous checkup actually help prevent failure and maximize that return on investment?
Because calibration is your best defense against data corruption. It stabilizes the sensor by correcting for all those minor internal shifts we discussed. But more importantly, it detects the early signs of stress or damage, like the subtle onset of nonlinearity from an unreported overload that a user would totally miss.
So you fix it before it becomes a crisis.
By detecting and correcting these minor deviations early, you prevent the premature failure and the subsequent scrapping of a very expensive and otherwise salvable load cell. It's pure investment protection.
This has been incredibly insightful. We've gone way beyond the common sense of just don't drop it. Let's bring this deep dive home with a final summary for you, the listener.
Let's do it.
So whether you're running a single test a week or hundreds of tests a day, extending the life and reliability of your load cell really boils down to 3 major proactive steps.
Step 1. Use the correct load cell for the job. Pay close attention to capacity oversizing and those critical environmental needs like temperature and IP rating.
Step 2. Protect it fiercely from mechanical trauma, physical shock, and electrical interference through diligent grounding and shielding.
And step 3, the most crucial one for maintaining decades of accuracy. Commit to regular, scheduled inspection and traceable calibration.
That's the path. That's how you get reliable performance and clean data. But before we go, we always like to leave you with one provocative thought to carry forward.
So you've talked a lot about load cells. These are exceptionally designed sensors built to perform accurately for millions of cycles, and yet they still require this scheduled annual intervention just to counteract natural drift and maintain their stability.
They drift even when they're perfectly designed.
Precisely. So it raises an important question for you to think about. What unseen sources of drift might be subtly impacting other complex data systems or measurements that you rely on every single day? Maybe it's your baseline data acquisition software or a predictive model you use or even your internal reporting standards. Is that system's 0 point shifting over time without you even knowing it? That's something worth tracking.